this lecture of the wave equation. Today I am going to solve few more questions related to the one-dimensional wave equation, and then I will try to find out the D'Alembert solution of the wave equation. So solve the question or string is tightly stressed at its ends and fasten at points x equal to 0 and x equal to L. Then the midpoint of the string is displaced transversely through through the distance B and then released from the rest so from that position. So now our aim is to find the displacement of the string at any time t greater than equal to 0. So find the displacement at some time at time t greater than equal to 0. So solution, here it is given that, say this is your u axis and that is your time t axis. Here our x is 0 and say this is your x axis and that is your u axis. So here your x is 0 and at this point say your x is L. So let us suppose that this is your O and this point is A. Now it is given that the midpoint of the string, now say the midpoint of the string is this point, that means this will be L by 2 comma 0. Now the midpoint of the string is displaced transversely, so through the distance B. Now if this string is displaced transversely at the distance B, then this will be your L by 2 comma B. So, and now from this position your string is released from its rest position. So find the displacement after some time t. So now to find the displacement of the string at some time t, let us find out the initial displacements, that means the distance OB and the distance AB. So the initial displacement means when the time is 0. The equation of OB is, this is your origin, so this will be your y minus y1, say this point 0, equal to y2 minus y1 upon x2 minus x1 into x minus x1. So from here we will get y equal to 2b upon L into x. So this is your displacement OB. Again, equation of AB is, say y minus 0 equal to y2 minus y1 upon x2 minus x1, then x minus x1. So this will be your y equal to, this will be minus L by 2, so this will be your 2b upon L, then your L minus x. So this is when your x is lies between 0 to L by 2, and this is when your x lies between L by 2 L. So you can say that at x equal to L, my y will be 0, and here at x equal to 0, my y is 0, and at x equal to L by 2, my y will be B. So thus we have the initial displacement, thus the boundary condition are so our boundary conditions are, the first point is initially when your time is 0, your displacement is 0, so ux naught is 0. Then when your distance is 0, then your u is 0. When your distance is L, then again your u is 0. Then initially we have released the string from the rest position, so that means the velocity of the string, the velocity of the particle will be 0 at time equal to 0. And the fourth condition is this one, the initial displacement. Here the initial displacement, that means when your time is 0, is given as 2bx upon L, when your x lies between 0 to L by 2, and then 2b upon L minus x, when your x lies between L by 2 to L. So now we have these four boundary conditions, and now with the help of these four boundary conditions, we will try to solve the problem. We will try to find out the displacement. So the solution of the wave equation is the general solution of the wave equation was C1 cos lambda x plus C2 sin lambda x, then C3 cos lambda ct plus C4 sin lambda ct. This was the solution of the wave equation. So this is equation number 1. And in the left hand side we have uxt. Now let us use the first boundary condition. Now u0t equal to 0 implies, that means when your x is 0, the displacement is 0. So if x is 0, then we will have C1 here, and then C3 cos lambda ct plus C4 sin lambda ct. So from here our C1 will be 0, because this bracket cannot be 0, otherwise the whole solution will be 0. So your C1 is 0, therefore your uxt C2 sin lambda x, and then C3 cos lambda ct plus C4 sin lambda ct. So now again use the boundary condition 2. Using the boundary condition u at t equal to 0 in equation number 2, we get, so now if your x is L, then again your displacement is 0. So if you put x equal to 0, then this will be your sin lambda L, and then we will have C3 cos lambda ct plus C4 sin lambda ct. Now again you can see that this bracket will be non-zero, otherwise your displacement will be 0. C2 cannot be 0, because if again C2 is 0, then the whole solution will be 0. So C2 cannot be 0, this bracket cannot be 0, that means your sin lambda will be 0. So from here our sin lambda will be 0, and you know that sin n pi is also 0. So the lambda will be n pi upon L. So your lambda is n pi upon L. So from 2, now we can put the value of lambda here. Before putting this value here, just use the boundary condition 3. Now using condition 3, using boundary condition 3, that means del 2 u upon del t x equal to 0. So if you use this condition, then before that we have to differentiate this equation with respect to t. So the differentiation of equation 2 with respect to t will be this will be a C2 sin lambda x, and here the differentiation of cos will be minus sin lambda ct. Then here we will have C4 lambda c, and the differentiation of sine will be cos lambda ct. Okay, now use the condition this one. That means when your time is 0, your initial velocity is 0. So this will be your 0 when time is 0. So this will be sine 0, and that will be a cos 0. Cos 0 is 1, sine 0 is 0. So we have sine C2 sin lambda x into C4 lambda c into 1. Now again, C2 cannot be 0, otherwise the whole solution will be 0. So that means your C4 is 0. So from here our C4 is equal to 0. Thus this C4 get vanished. Therefore the solution, therefore uxt will be equal to, now C4 is 0, so we will have C2 into C3 sin lambda x cos lambda ct. And the most general solution will be, the general solution is uxt equal to summation n equal to 1 to infinity cn sin lambda x into cos lambda ct. This is your solution, say your n equal to 0. Now this will be the solution of, again here your lambda cannot be, here your n will be from 1 to infinity, otherwise this term will get vanished. So this is your most general solution of this wave equation when your initial velocity is 0, and this is common for all the problems where my lambda is n pi upon l. Okay, where my lambda is n pi upon l, or we can say that uxt equal to n equal to 1 to infinity cn, put the value of lambda, sin n pi x upon l into cos n pi ct upon l. So this is the most general solution of the wave equation when the initial velocity is 0. Now if the initial velocity is non-zero, then we will use different technique, but when the initial velocity is 0, this will be the solution for all the problems. Now let us use this condition, boundary condition 4. Now using boundary condition ux0 equal to 0, that means when your time is 0, your displacement is 0. So in the left hand side we will have ux0, and ux0 has these two values, and in the right hand side we have n equal to 1 to infinity cn sin, now because our t is 0, so cos 0 will be 1, so we will have n pi x upon n. So this is your ux0. Now here we can see that the right hand side is your half range sine series. Now if this is your half range sine series, then fx equal to some n equal to 1 to infinity cn sin n pi x upon l. So if this is your half range sine series, then the coefficient, the Fourier coefficient will be, so cn will be 2 upon l, 0 to l, fx means ux0 into sin n pi x upon l into dx. So this will be your the value of the cn. Now ux0 has two values. One, when your x lies between 0 to l by 2, ux0 has value 2bx upon l, and when your x lies between l by 2 to l, our ux0 is 2b upon l into l minus x into dx. Now use the Bernoulli rule of integration. So this will be your 2 upon l from here we will have 2b upon L. Now the integration of this one will be x into integration of sine will be minus cos n pi x upon L. Then the coefficient will be L upon n pi. Then we will have differentiation of x as 1, and again the integration of cos will be sine n pi x upon L into L square upon n square pi square. So this is the integration of the first term, and the limits are from 0 to L by 2. Then integration of second term will be plus, here we will have 2b upon L common, and then in the bracket L minus x, then the integration of sine will be minus cos n pi x upon L into L upon n pi. Then we will have minus sign, and the differences of L minus x will be minus 1, so this is your plus, and again we will have sine n pi x upon L into L square upon n square pi square, and the limits are from L by 2 L. Okay, now let us put the limit here. If your x is L by 2, then this will be your cos n pi by 2. Here you can see that if your x is L by 2, then this L will get cancelled, and we will have this one as cos n pi by 2. And if x is 0, then this term will be 0. This term will be 0 for both the limits, because if x is L by 2, then this will be your sine 2n pi, and sine 2n pi is 0. For the lower limit it is sine 0, which is 0. Again this term will be 0 for both the limits. For the upper limit this will be your sine n pi, and that will be 0. And for the lower limit this will be your sine 2n pi, and again that is 0. This one for the upper limit is 0, and for the lower limit this value will get adjusted. So we have 2 upon L. Now from here we will have 2b upon L, then the value of x for the upper limit is L by 2. Now this will be your, now if your x is L by 2, so if your x is L by 2, then this will be your cos 2n pi, and cos 2n pi is 1, so this will be your minus 1, and we will have L upon n pi. So this is the upper limit of this one, and lower limit is 0. Now coming to this term, this will be 2b upon L. Now if your x is L by 2, that means the lower limit, so we will have the minus sign. Now if your x is L by 2, then again it is your L by 2, and this will be your, if your x is L by 2, here I have made a mistake, if x is L by 2, then this will be cos n pi by 2, not minus 1. So we will have 2b upon L, then the value of x is L by 2, and now because, and again here if your x is L by 2, then this will be your sine n pi by 2, so this term will get adjusted. And now coming to this term, if your x is L by 2, then this will be your cos n pi by 2. Now if n is 1, then this will be cos pi by 2. If n is 2, so let us write this term. So this will be your minus cos x is L by 2, so this will be cos n pi by 2. Now if your n is 1, then this will be 0. If n is 2, then this term will get adjusted. So, and for the lower limit it is 0. Now here this will be minus minus plus, and now this will be your 2b upon L into the upper limit. The upper limit will be, and this is your minus minus plus. Now if your x is L by 2, then this will be your sine n pi by 2, and into L square upon n square pi square. Okay, then coming to this point, the upper limit is 0 and the lower limit will be minus 2b upon L. If you put x equal to L by 2, then this will be your L by 2, and again 1 minus sign is here, so this will be your plus. Now again this will be your cos n pi by 2, because x is L by 2, So this will be your n pi by 2 into L upon n pi. And again we have a term L upon n pi here. L upon n pi plus 2v upon L. So now coming to this point, if your x is L, so the upper limit will get vanished because this will be your sin n pi, and for the lower limit we will have sin. Now if your x is L by 2, so this will be your sin n pi by 2 into L square n square pi square, and the coefficient was 2v upon L. Again in this case the coefficient was 2v upon L, so we will have into 2v upon L. Okay. Now let us see how many terms are getting cancelled. So this term is cancelled with this term, and then these two terms will get merged because this is your 2v upon L, this is your 2v upon L. So we have Cn equal to, therefore your Cn equal to 2 upon L. Now these two terms are common, so we will have 2 times 2v upon L sin n pi by 2 into L square n square pi square. So now this L square will get cancelled from this L square. Now this will be 2 to the 4 to the 8, so we will have 8b upon n square pi square into sin n pi by 2. So this is your Cn, and let me cross check this Cn. So our Cn is 8k 8b upon n square pi square sin n pi by 2. So this is your solution. Now here you can see that if your n is 2, that means if n is 2 or 4 or 6 or 8, then this term will be 0. So we will have the values only for the odd terms. Therefore your solution will be, your uxt will be n equal to 1 to infinity Cn. Cn means 8b upon n square pi square sin n pi by 2. Then the term was Cn sin n pi x upon L into cos lambda pi ct upon L. So this is your answer. So this is the solution of the problem. So let us solve one more question. Now in this problem your initial displacement will be 0, but now we will have the non-zero value of the initial velocity. So question, this is your question of different type. Here a tightly stretched string with fixed point with fixed points at x equal to 0 and x equal to 50 is initially at rest in its equilibrium position. So that means in this case your initial displacement is 0, and now if it is set to vibrate, by giving each point of velocity and the initial velocity is, by giving each point initial velocity v naught sin pi x upon 50 into cos 2 pi x upon 50. So if this is your initial velocity, then find your displacement at any time t equal to t naught greater than t not equal to 0. So find your displacement at any subsequent time. So a tightly stretched string with fixed point at x equal to 0 and x equal to 50 is initially at rest in its equilibrium position. Now that means your initial displacement is 0. Now we have given a initial velocity to the string, and then if it is your initial velocity of the string of some point, then find the displacement at any time t. So solution. The solution of the wave equation is xt equal to c1 cos lambda x plus c2 sin lambda x, c3 cos lambda ct plus c4 sin lambda ct. The boundary conditions are initially when your length is 0, your displacement is 0. Then when your length is 50, again your displacement is 0. Now in the third case, the initial displacement of the string is 0. So this is your different from the last question. Now here we have the initial velocity at b naught sin pi x 150 into cos 2 pi x 150. So this is your initial velocity of the particle. Okay, now let us operate these boundary condition using one, as in last problem. If you use this u0 t equal to 0, that means when your x is 0, then this will be your sine 0, and we will have, as in last question, we will have c1 equal to 0, because if we put x equal to 0, then this will be c2 sin lambda 0, that means sine 0 is 0, so we will have c1 cos lambda x into this term. So from here we will get c1 equal to 0, and if you use this condition u50t equal to 0, then now c1 is 0, so in the left hand side we will have 0, and here we will have c2 sin 50 lambda and c3 cos lambda ct plus c4 sin lambda ct. So again you can see that c2 cannot be 0, otherwise this whole solution will get 0. So from here sin 50 lambda will be 0, and we know that this is your sin n pi. So lambda will be n pi upon L, that L is 50. So this is your lambda. Now let us operate the condition number 3. Again, our initial displacement is 0. So this will give you, when t equal to 0, your u is 0. c1 is already 0. So this will be your c2 sin lambda x. Now t is 0, that means cos 0 is 1 and sin 0 is 0. So we will have c3. So c2 cannot be 0, so c3 will be 0. Therefore your uxt will be, now our c1 and c3 are 0. So this will be your c2 sin lambda x into c4 sin lambda ct. Therefore the most general solution is uxt equal to summation n equal to 1 to infinity. Then we will have sin, the value of lambda was n pi upon 50 into sin lambda. Now c3 is 0, so this will be your sin lambda. Again our c3 is 0, so we will have sin n pi ct upon 50. So this is the solution of the wave equation. Now let us use the fourth boundary condition. That means when the initial velocity is given and that is non-zero. So on differentiating this equation with respect to t, we will have sin, cn is here, cn sin n pi x upon 50. Then the differentiation of sin will be your cos. n pi ct upon 50 into the coefficient of differentiation n pi c upon 50. Now given that this initial velocity is given that del u upon del t when your time is 0 is equal to v naught sin pi x upon 50 into cos 2 pi x upon 50. So using this condition, we have v naught equal to v naught sin pi x upon 50 into cos 2 pi x upon 50 is equal to, now because t is 0, so this term will get vanished. So from here we will have n equal to 1 to infinity cn sin n pi x upon 50 multiplied by n pi c upon 50. Now this term can be written as v naught upon 2. Now 2 times sin a into cos b will be sin a plus b, that means sin 3 pi x upon 50 plus sin a minus b, that means this will be minus sin pi x upon 50. And in the right hand side we have pi c upon 50, and in the bracket we have cn into n sin n pi x upon 50. So let us equate the coefficients. Now you can see that if your n is 1, then we'll get sin pi x upon 50. So if n is 1, then in the right hand side we will have pi c upon 50, and if n is 1, this will be your c1 and this will be your sin pi x upon 50, and the coefficient of sin pi x upon 50 in the left hand side is minus v naught upon 2. So from here our c1 will be minus 25 v naught divided by pi into c. So this is your coefficient c1. And similarly, if we take n equal to 3, then in the right hand side we will have pi c upon 50 into 3 into c3, and now the coefficient sin 3 pi x upon 50, and in the left hand side it is v naught upon 2. So from here our c3 will be 25 divided by 25 v naught divided by 3 pi c. So this is the coefficient c3. Therefore your solution is, our uxt was n equal to 1 to 1 infinity cn sin n pi x upon 50 into sin n pi ct upon 50. This was the solution. Now we have only two values of c1. We have only two values of cn. One is c1 and another is c3. So let us put the value of c1 as minus 25 v naught upon pi c. Then this will be your sin pi x upon 50 into sin pi ct upon 50. And the another coefficient will be when your n is 3, that means c3. And the value of c3 is 25 v naught upon 3 pi c. And then this will be your sin 3 pi x upon 50 into sin 3 pi ct upon 50. So this is the solution of this one-dimensional wave equation. So this is our solution. D-element solution of one-dimensional wave equation. So consider the wave equation, that means the one-dimensional wave equation, as del u upon del t2 equal to c square del u upon del x2. Let us assume that this is your one-dimensional wave equation. Now for the D-Lambert solution, we will try to remove this wave equation in its normal form. For that we need the transformation. Let v equal to x minus ct and w equal to x plus ct. That means now our function u will be a function of, will depend on these two new variable. That means earlier our u is a function of, was a function of x and t. Now we are converting these x and t in the new variables v and w. So therefore your del upon del t, or you can say del u upon del x, will be del u upon del w into del w upon del x then del u upon del v into del v upon del x. So from here you can see that your del w upon del x is 1 and del v upon del x is again 1. So we can also write it as del u upon del v plus del u upon del w, because both del w upon del x and del v upon del x are 1. So from here the operator del upon del x will be del u upon del v into del upon del v into del upon del w. Therefore the second order derivative will be del by del x of del u by del x. So that means it is equal to del by del v of plus del by del b plus del by del w of this del u by del x. So now here you can see that this is your double derivative. This will be your del 2 upon del v del w. This will be your del 2 u upon del w del v. And as these two are equal to each other, so we can write it as del 2 upon del v2 plus 2 times del 2 u upon del v del w plus del 2 u upon del w2. So this will be the value of del 2 u upon del x2. Now let us find out the value of del 2 u upon del t2. Now similarly your del u upon del t will be del u upon del v into del v upon del t, del u upon del w into del w upon del t. So here you can see that the value of del v upon del t is minus c and the value of del w upon del t is plus c. So we will have plus c common, del u upon del w minus del u upon del v. So from here the first order derivative will be c times del upon del w minus del upon del v. So the double derivative will be, so therefore the double derivative is equal to del by del t of del upon del t. So del by del t is this one and del upon del t is this one. So this will be your c square del by del w minus del by del v of del upon del w minus del upon del v. So from here this is equal to c square del t upon del w2 minus del t upon del w del v, and this will be your 2 times, and then we have del 2 u upon del v2. So this is the value of del t upon del t2. Therefore by wave equation let us put these two values in your wave equation. So we will have c square, now del t upon del t2 is this one, c square del t upon del w2 minus 2 del t upon del w del v plus del t upon del v2, and this was your, I think this was your del t upon del x2 was del t upon del w2 plus 2 del t upon del w del v plus del 2 upon del v2. So from here you can see that this term and this term is cancelled. This is okay. Now from here you can see that the first term and the last term are cancelled. So the second term will give you, so from here we will have, now this is minus 2 if you take this in the right hand side. So we will have 4c square del 2 u upon del w del v equal to 0. So c cannot be 0, that means del 2 square del v del w equal to 0. Now let us integrate this term with respect to v. On integration with respect to v, as we are integrating partially with respect to v, so this will be your del upon del w equal to some function of w, because we are integrating with respect to v, so that means this has to be some function of w. Otherwise if you write it as a some function of v, then this double derivative will not get 0, because if you differentiate this one with respect to v, so as we are differentiating this one with respect to v and it is a function of w, so your right hand side will be 0 and we will get this term. So on integration with respect to v, we will get a function of psi, we will get a function of w. Again integrating, again on integration, now this will be your some integration of w with respect to w, plus we will have some another function of v, say your phi v. So now this is again a function of w, so we can write it as say f of w plus phi of v, and now w was your x minus ct and phi is your and v was your x plus ct. So this solution is known as, now this is known as the normal form or canonical form of the wave equation, and this is your u equal to phi of x plus ct plus some another function x minus ct. This is known as your D'Alembert solution of the wave equation.